So this video is related rates day one. Yesterday, we started looking at the idea of finding the rate of change of y with respect to t in terms of x with respect to t. So this idea of differentiating with respect to some other variable. And we talked about how we could express dy dt in terms of dx dt. And if we were given a little bit more information about how x was changing with respect to t and a particular x and y value, then we would be able to evaluate that a little further. So that's kind of where we're going to pick up today with this first example. If you take a look at problem number 1, it says that suppose that y equals 5x squared minus 6x plus 2. Find dy dt when x is 4, given that dx dt equals 2 when x is 4. So again, notice that we are differentiating this time with respect to t. And t is not actually a variable that is defined in our function. So we're going to start this off the same way we did yesterday. We're going to take the derivative of everything in this equation with respect to t. So first I'm going to take the derivative of y with respect to t, which just gives me dy dt. Then I need to take the derivative of each term here on the right side with respect to t. So if I take the derivative of 5x squared with respect to t, then I'm going to get 10x times the derivative of x with respect to t, dx dt, minus, then I have 6x, so when I differentiate that with respect to t, I get 6 times the derivative of x with respect to t, dx dt, plus the derivative of 2 with respect to t will just be 0. So yesterday at this point we said, okay, well both of these have dx dt, we could factor the dx dt out, and then we would be finished at this point. We would have dy dt in terms of dx dt. But that's not really what they're asking for in this problem. Instead, they went ahead and gave us some additional information. They want us to find dy dt such that x equals 4. And they are telling us that when x equals 4, dx dt is equal to 2. So we can take that information and we can plug it directly in. We want to know what is dy dt such that x is equal to 4. And we know that we would have 10 times x is 4. And we know that when x is 4, dx dt is going to be 2. So we could go ahead and take that 2 for dx dt and substitute that in directly. Minus 6 times, and again, when x is 4, dx dt is going to be 2. So we can put that right on in. So I've got, what, 10 times 8 is 80. Minus 6 times 2 is 12. So I'm going to get 80 minus 12 would be 68. So this is again just kind of like the problem that we left off with yesterday, except now they've done a So now we're going to take that a step further. In this next example, they've told us that a pebble is dropped into a calm pond, causing ripples in the shape of concentric circles. The rate of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, find the rate at which the area of disturbed water is changing. So I like to start these problems by looking for some kind of information about a rate of change. Because really what we're looking for is when we change one particular thing, how does it cause something that is related to it in some way to change as well? And then we're looking at how it into a pond. So we kind of have a pebble thrown into the water and it makes a ripple in the shape of concentric circles. Concentric circles just means like you have circles with the same center. So we kind of have these waves that are radiating out from the center of this circle. They tell us that the outer ripple, so that outer ripple would be in the shape of a circle, that its radius is increasing at a constant rate of 1 foot per second. So they've given us a rate of change. Specifically, they've given us the rate of change of the radius, so we'll call it the change in the radius, dr, with respect to time. And so we'll use the variable t for time. We know it's with respect to time because they've told us 1 foot per second. So they're telling us with respect to our change in time, which in this case would be in seconds. And they've told us that it is increasing at a rate of 1 foot per second. So dr dt is 1 foot per second. Notice that it's positive here because if it is increasing, then we would have a positive rate of change. So if we go back to our water drop here, this circle again represents the outer ripple as the area of disturbed water is increasing. And they've told us that the rate of change of the radius, r, of that outer ripple is 1 foot per second. So then they've asked us, when the radius is 4 feet, to find the rate at which the area of disturbed water is changing. So they've given us the rate of change of the radius with respect to time, and they're asking us to find the rate of change of the area of disturbed water with respect to time. So I'm going to find the rate of change of the area of that circle, we'll call it A for area, with respect to time. And specifically, they want us to do so when the radius is 4 feet. So when the radius r equals 4 feet. So they've given us the rate of change, and they're asking us for another rate of change. So in order to relate these two rates of change, we're going to have to go back to some kind of relationship between those two variables. So we're looking for a relationship between the radius of this circular region on the water and its area. And so the relationship that we know about the area of a circle to its radius is that the area of a circle is equal to pi times the radius squared. But I'm not directly relating the area and radius, but rather I'm looking at the rate of change of the radius and the rate of change of the area. And I'm doing so with respect to time. So I don't necessarily know what the radius and area are, but what I do know is the rate of change of the radius with respect to time. And what I want to know is the rate of change of the area with respect to time. So that means that I'm going to take the derivative of everything in this equation with respect to time. So when I do that, I have the rate of change of A with respect to t. Well, that would just be dA dt is equal to pi times the radius squared, and we're going to take the derivative of that with respect to t. Now, pi is just a constant, so when I take the derivative with respect to t, I'm going to get 2 pi times the radius times the derivative of the radius, dr, with respect to time, dt. So now we've taken the relationship that we know involving area and radius of a circle, and we've come up with the relationship between the rate of change of the radius with respect to time and the rate of change of the area of that circle with respect to time. We want to know what is dA dt when radius is 4 feet. And we also know that the rate of change of the radius with respect to time is going to be 1 foot per second. So I want to know what is dA dt when the radius is 4 feet. So such that the radius is 4. Well, I'd have 2 times pi times the radius would be 4 feet. And we know that the rate of change of the radius would be 1 foot per second. So then we have that dA dt would be 2 times 4 gives me 8. So 8 pi. We also want to make sure that we include units on this. It would make sense that if our radius is in feet per second, or our rate of change of our radius is in feet per second, if we're measuring our radius in feet, then our area, its rate of change, would be square feet per second. If you're not sure though what the units should be, go back to your original equation and look at what you're putting in. We have 2 pi, and if we include the units, we have 4 feet for the radius times 1 feet per second. So that feet times feet would give us the feet squared that we would expect to see for area, and our time would be measured in seconds. So then I like to wrap these problems up just by kind of writing out a sentence of what's changing and how it's changing with units. So in this case, dA dt is the rate of change of the area. We can say that the area is, and we want to make sure that we include how it's changing, because as a positive rate of change, we would say that the area is increasing at a rate of 8 pi square feet per second. So again, we want to start with looking for the rate of change that we're given, the rate of change that we're going to find. If we need a picture, we want to make sure that we draw that too. In this case, having the picture of the circle probably wasn't too beneficial, but in more complicated problems, having a picture where we can kind of see what's happening might help us set up our relationship between the rate that we know and the rate that we're looking for. So then we want to find some kind of relationship that exists between those. Then we can differentiate with respect to whatever it is that we're looking at changing. And then we can start to go back and substitute things in based on the information that we're given. All right, let's go ahead and take a look at one more. In example 3, it says that water runs out of a conical tank at a constant rate of 2 cubic feet per minute. The radius at the top of the tank is 5 feet, and the height of the tank is 10 feet. How fast is the water level sinking when the water is 6 feet deep? So I'm going to go ahead and draw a picture of what's happening. We have a conical shaped tank where water is running out. So I'm just going to draw like a tank shaped like a cone. And this tank has some water in it. And the water is running out of that tank. And it says that it's running out at a rate of 2 cubic feet per minute. So water runs out at a rate of 2 cubic feet per minute. So they've given us a rate of change. That's going to be what we're given. And they want to know how fast is the water level sinking when the water is 6 feet deep. So when we see that how fast is something changing, we know that that's going to be the rate that we're looking for. So we're talking about how fast the amount of water in the tank is changing. And when we're talking about the amount of water in a tank, in a conical shaped tank, then we're talking about the volume of the water. So they have given us the rate of change of the volume of the water in the tank. So I'm going to call that dV dt, the rate of change of the volume of the water with respect to time. They've told us that the water is running out at a rate of 2 cubic feet per minute. Now in this case, because the water is running out of the tank, that means that the volume of the water should be decreasing. So we need to make sure that our rate of change reflects that. Since the volume of the water is decreasing, we know that we should have a negative rate of change for the volume of the water with respect to time. And then we want to know how fast is the water level sinking. So when we're talking about the water level, if we come back over here, we're talking about the deepness of that water. So maybe we'll call this H for the height of the water. So they've given us dV dt, and we're asked to find the rate of change of the height of the water. So since I called it H here, then that means that we are going to find the rate of change of H, the height of the water, with respect to time. And specifically, we want that when the water is 6 feet deep. So when the depth of the water, which we're calling H, is equal to 6 feet. So we drew our picture, we took the information, the rate that we were given, the rate of change that we're trying to find, and now we want an equation that's going to relate those two. So I'm looking at water in a conical tank, and the volume of that water, the volume of any cone, is going to be 1/3 times pi times r squared times h. And so we have an equation here that's going to relate the volume of the water, that cone shape, to the height of the water. But in doing so, we've kind of created another issue. Because notice that the volume isn't just dependent on the height of the water. The volume is also dependent on the radius of that tank. And while we know, or the radius of the water, and while we know the radius of the tank, they've told us that the radius at the top of the tank is 5 feet. We don't really know what the radius of the region with the water is going to be, because that's going to depend on our water level. As our water is running out, the height is going to be decreasing. The radius is also going to be decreasing. So what we're going to have to do is we're going to have to take our variables here, r and h, and we're going to have to come up with some kind of relationship that is going to allow us to eliminate this r. So we have an equation that's solely in terms of v, the rate of change that I know something about, and h, the rate of change that I'm looking to find something out about. So let's go back to our problem and see if there's any more information they give us that we can use. We said that the radius at the top of the tank is 5 feet. They've also told us that the height of the tank is 10 feet. So the height of the whole thing is 10 feet. And that's the information that we're going to use to eliminate the variable. Because if you look at the picture that we've drawn now, I'm just going to kind of sketch what we've got here. Notice that we have kind of two triangles that are being formed here. We have this larger triangle where we know the radius of the whole tank, 5, and the height of the whole tank, 10. But then we have this smaller triangle that's kind of embedded in it, where our height and our radius are changing again as the water is running out. So what we have here, there's my big one, 10 feet, 5 feet. And here's my little one, we're calling the height of the water h, and the radius of the water r. What we have are two similar triangles. And if you remember from geometry, triangles that are similar are going to be proportionate to one another. So I can set up a proportion that's going to relate the r value, the radius of the water, and the h value, the height of the water, to this similar triangle that has a radius of 5 and a height of 10. In other words, the proportion r over h, radius to height, of our small triangle will be proportionate to the radius of our larger triangle, which is 5, and the height of our larger triangle, which is 10. Or we reduce that 1 over 2. So if r over h is equal to 1/2, then that means that the radius would be equal to 1/2 times the height. And now what we can do is we can take that information about the radius being equal to 1/2 the height. We can go back to our equation relating volume to radius and height. And we can now substitute in this information for the radius. So the volume then is equal to 1/3 times pi times the radius, which is going to be half of the height squared, times the height. So then the volume is 1/3 times pi times 1/2 squared, 1/4, times h squared times another h. So then the volume, if I simplify this a little bit, I have 1 times pi times 1 is pi, over 3 times 4 is 12. And then I have h squared times h gives me h cubed. So I've taken my volume formula that related both height and radius, and I've simplified it down to the two variables I'm interested in. I know something about the rate of change of v, and I want to know about the rate of change of h. And so those are the two variables that I'm looking to relate. Now I'm ready to relate those two rates of change. So if v is equal to pi over 12 times h cubed, then if I want some relationship between v dt and dh dt, then I can take the derivative of everything with respect to t. So I have the derivative of v with respect to t, which is dv dt, is equal to pi divided by 12 times h cubed. So when I take the derivative of that, I'm going to have 3 over 12, or pi over 4. Decrease the power of that by 1, so h squared, times the derivative of h with respect to t. Look out, cat. So now I have something that's relating my rate of change of my volume with respect to time and my rate of change of my height with respect to time. And I'm wanting to know what is the rate of change of the volume with respect to time, or the rate of change of the height with respect to time, when the height is equal to 6 feet. I know that the rate of change of the volume with respect to time, dv dt, is -2 cubic feet per minute. We'll go ahead and put our units. Cubic feet per minute. I have pi over 4, and I'm interested in the rate of change of the height when the height is 6, so 6 squared there, times dh dt is what I'm looking for. And again, that would be in 6 feet. We'll put that feet in there. So then I have -2 cubic feet per minute is equal to, let's see, 6 squared would be 36, divided by 4 would be 9, and 9 times pi, and I've got feet squared, times the h dt. So I'm going to divide everything by 9 pi square feet. So I get that dh dt is equal to -2 divided by 9 pi. Just want to make it clear that that's negative, so clean that up a little. -2 divided by 9 pi. And notice I have cubic feet divided by square feet leaves me with feet per minute. And that makes sense. We're talking about the rate of change of the height. So we would expect our height to be measured in feet. So our rate of change of our height with respect to time would be in feet per minute. So a few things that I want to point out, because this is a really common mistake. First off, notice where the pi is. The pi is in the denominator. This is 2 divided by 9 pi. A lot of times I see people that do this. If you write your answer that way, it's not clear whether you're saying 2 over 9 times pi or 2 over 9 times pi. In other words, is the pi in the denominator or not? So be really careful about how you write your answer. If your pi should be in the denominator, and in this case it should, make sure it's really clear where that is. So this is 2 over 9 pi with the pi in the denominator. Another thing that I want to point out is notice that we ended up with a negative value here, which means that the height is decreasing. So if we think about our original problem, by the time we get to the end, our answer should make sense for the problem. And in this case, the water is running out of the tank. So if the water is running out of the tank, it stands to reason that the height of that water should be going down, should be decreasing. And that's exactly what we're seeing in our final answer, that height would be decreasing because we ended up with a negative. So I'm just going to finish this problem up by writing out my answer in a full sentence. So in this problem, the height of the water is decreasing at a rate of 2 over 9 pi feet per minute. We said what was changing, we said how it's changing, we said by how much, and we included the units. So make sure that you do all of that in your final answer.